Math 1314, section C87, homework 8, functions and relations, video 5, applications, questions 20 through 24. Normally applications mean word problems, but in this instance, it does not always mean word problems. Allow me to explain. Okay, well, this first one is number 20. Joe rides his bicycle on average 20 miles per hour. The distance Joe rides, d of t in miles, is given by d of t equals 20t, where t is the time in hours that he rides. Evaluate d of 5 and interpret the meaning. Determine the distance Joe travels in 34 minutes. Give the exact answer. Do not round. So what the heck is going on here? Well, functions often model real-world scenarios where the input and the output mean something. And when you're given a function, you should be told what the input means and the output means. Here, our function is d of t. They won't let me highlight it, but it's right there next to the s. Our function is d of t. And since the input is t, which usually stands for time, we're told that where t is the time in hours that he rides. So we're going to put in how many hours you ride. And then when it says Joe rides, the distance Joe rides, d of t in miles, means that the output is going to be miles. So it's not uncommon for a function to have a meaningful input and output. In this case, we're saying d of t equals, it was 20t. Where the input is the hours ridden. And the output is the distance traveled. That's why the function is called d. If your input and output have meaning, then we can calculate distance traveled based on hours ridden, or it might even be able to calculate hours ridden based on distance traveled. And that's actually what this question is asking. On A, it says evaluate d of 5 and interpret the meaning. Well, evaluating d of 5 is easy. Our function says, give me a number and I'll multiply it by 20. And we could also use the gimmick where we replace the t with parentheses and then just fill it in with whatever's over there. 20 times 5 is 100. But keeping in mind that the input is hours and the output is distance traveled, specifically miles. That means in 5 hours, we traveled 100 miles. On a bike, I guess that's not unfeasible. D of 5 is equal to 100. Thus, Joe travels 100 miles in 5 hours. So it's just a function used in a real world situation, which is sometimes called a model. Joe travels blank miles in 43 minutes. Well, this one is tricky because they're giving us the time that he traveled, but what do you notice about it? It's 34 minutes, but it says up here that our t is time in hours, but our time is given in minutes. So how do we find the time traveled? Excuse me, how do we find the distance traveled when the input is asking for hours ridden? Well, t equals 36, no, it's 34 minutes, I believe. How do you turn minutes into hours? Well, you divide. 34 over 60 would give you the number of hours, because there are 60 minutes in an hour. So for example, if we had 120 minutes, we would divide by 60 to turn it into 2 hours. But the fact that it's 120 doesn't change that. We divide by 60 to turn minutes into hours. Or think of it this way. If we measure the same amount of time in minutes versus hours, the number of minutes should be more because a minute's a smaller unit of time. So when we turn minutes to hours, we need to turn that number to a smaller number. So if it's between multiplying by 60 or dividing by 60 would turn into a smaller number. Now, can we divide this out and make it a decimal? It won't end. Can we make it a fraction and reduce it? I would. We can reduce this by 2. 34 divided by 2 is 17. 60 divided by 2 is 30. So it's that many hours. And so our function asked us the number of hours traveled. It would be 17 over 30. And our function says, I'm going to multiply 20 times whatever you have in there. And now it's a game of, do we know how to do this? Well, to multiply a whole number times a fraction, just turn the whole number into a fraction by putting it over 1. And at this point, you can either multiply or reduce. The rule for reducing is any number on top can reduce with any factor on top. Part of a multiplication problem can reduce with any factor on the bottom. In this case, the 20 and the 30 can both be reduced by 10. 20 divided by 10 is 2. 30 divided by 10 is 3. And now we can just multiply straight across. 2 times 17 is 34. And on the bottom, 1 times 3 is 3. And that measures miles. So let's see if that's the answer they wanted. If I can get back to it. We had, I forgot what it was. We had, where's the, hold on, folks, losing things here. We had 34 thirds miles, and it should accept that. It should accept 34 thirds because, well, it didn't tell us how it wanted the answer, except it wanted to give the exact answer, do not round. And that exact answer, I forgot it again. Worst short-term memory ever. 34 over 3. 34 over 3. Come on, let me share. 34 over 3. And if we type 34 over 3, let's see if it'll take it. Oh, it did. I bet it would have accepted a mixed number also. All right, so this is an example of an application. Now, some of these applications are pretty easy. Like number 18. Refer to the function determine f of 7. We've already seen a problem like this. In terms of ordered pairs, the input is the x, the output is the y. I swear we've already done this one. So when I put in 7, it's asking what comes out. Well, the ordered pair 7, 2 says that when 7 goes in, 2 comes out. Just remember, every function input and output combo is an ordered pair, is an ordered pair. 18 is the one we just did. I didn't check it. Okay, now let's do 19. 19 is kind of the same thing, but it's a little bit backwards because notice they're asking for what value of x is f of x equal to 2. In other words, they're saying what input gives an output of 2. But the output is the y coordinate and the input is the x coordinate. So they're saying what x is paired with 2. Well, look at the last ordered pair, -5, 2. -5 is paired with 2. It's the only number paired with 2. So the only value for x that goes in and comes out as 2 is -5. Just remember, every function input and output pair is an x and a y. So if you have half of the input output pair, you have half of an ordered pair, you go look for the ordered pair that matches. And I believe, oh, this went through 24. Oh, that's the problem. I was looking at the wrong problem, I believe. I was supposed to look at 20 through 24. Hold on, folks. Why is this not sharing? 20 through 24. Having issues, folks. Wouldn't be the first time today. Okay, there's that. There's that. All right. Yeah, we just number 19. No wonder that looked familiar. I'm not going to restart the video, but 21 through 24 is what we're supposed to look at. Oh, determine the x and the y intercepts. I believe 20, 21, 22, 23 are all find x and y intercepts. 24 is another word problem, which I'm not going to go over. I'll leave it up to you to take a look at it. But I do want to talk about 21 through 23, which is finding x and y intercepts of a function. We kind of talked about this in class today, but not from a function perspective. We'll do this one. R of x equals -square root of x plus 2. Next page, please. R of x equals -square root of x plus 2. And the question is to find the x and y intercepts. Now, what we already learned in class earlier today, for those of you who were here, that the y-intercept is when x is equal to 0, and the x-intercept is when y is equal to 0. So to find these intercepts, we just have to take turns letting the correct input or output be 0. For example, for the y-intercept, whoa, that's horrible spelling there. We let x equal 0, but in the function, the x is the input. So we just have to say, all right, x becomes 0, and let's see what we get. -square root of 0 plus 2. The square root of 0 is 0, but we haven't done the negative yet. The negative of 0 is 0. It's the only number that's equal to its opposite. And 0 plus 2 is 2. So if we combine the input with the output into an ordered pair, that means our our y-intercept is 0, 2. For the x-intercept, we pretty much do the same thing. Give me a second to clear this mess up, and we'll do the x-intercept. Okay, to find the x-intercept, we let y equal 0. But where is the y in a function notation problem? The answer is the y is the output. So we need what's coming out to equal 0. So we need to solve negative square root of x plus 2 is equal to 0. This is a pretty easy thing to solve. It's just a radical equation. We talked about solving them. Our first move is to isolate the radical. We can start by subtracting 2 from both sides to get negative square root of x equals negative 2. And then to finish isolating the radical, we can divide both sides by negative 1. Let's move it up here. That would give us the square root of x is equal to 2. And then to get rid of the radical, we would raise both sides to the second power. And that would cancel the square root and give us 4. Technically, we should check that answer to make sure it does come out 0. But it's pretty obvious if we put a 4 right there, its square root is 2, stick a negative on it to get negative 2, and then add 2 to give us 0. So that is going to be the x that produces a y value of 0, which means our x-intercept is 4, 0. But in general, to find the y-intercept, you put 0 in, and to get the x-intercept, you force 0 out, which is the same as putting the function equal to 0. And that's the end of this video.